Hi folks! Today we are going to explore the front panel from a Sony compact disc receiver model HCD-BX20i. This panel uses a fluorescent indicator tube, often abbreviated as FIT, also known as a vacuum fluorescent display or VFD. The display is controlled by a driver from Princeton Technology Corporation, reference PT6302. We have already covered the PT6302 on the channel, and one of its biggest advantages is how easy it is to use. The driver supports the direct use of the ASCII character table, which greatly simplifies the process of displaying text. In practice, if we want to show a message on the display, we simply send the text itself, and the driver takes care of presenting the characters correctly. As usual, we use an Arduino Uno to control the driver. For this project, we use pins 8, 9, 10 and 11, assigned respectively to data, clock, chip select, and reset. And, of course, we must not forget the common ground reference between the Arduino and the panel. The code used here is relatively simple. With only a few modifications, it becomes very easy to give this panel a second life. The power supply arrangement is also quite straightforward. This panel already includes its own DC to DC converter, which generates both the filament voltage and the VEE supply voltage. According to the service manual, which is available online, the VEE voltage is approximately minus 22.8 volts DC. If we want to use all of the panel's original features, we must provide 3.3 volts DC to pin 2. It is worth noting that this 3.3 volt rail is only used to power the standby LED and the infrared receiver. The PT6302 itself is powered differently. A voltage of 4 volts DC is applied to pin 13. This voltage passes through diode D915, causing a voltage drop of approximately 0.7 volts. As a result, the driver's VDD pin, which is pin 56, receives approximately 3.3 volts DC. One interesting detail in the design is the additional biasing applied to grid 1. This is achieved through transistor Q905. The purpose is to compensate for the slightly larger phosphor area on that grid, helping to maintain uniform brightness across the display and preventing visible fluctuations. According to the design specifications, the maximum segment current is approximately 3 mA, with all segments illuminated and a VDD voltage of 3.3 volts. Now let us take a closer look at the DC to DC converter used on the panel. The converter receives 9 volts DC through the center tap connection, which is pin 3 of the transformer. The outer connections, pins 2 and 4, are switched by a dual transistor arrangement identified as Q903. Oscillation is produced through a feedback winding connected to pins 5 and 6 of the transformer primary. On the secondary side, the transformer provides AC voltage for the filament through pins 7 and 8. The VE voltage is generated separately through a full-wave rectifier connected to another winding, using pins 1 and 9. The filament reference is then established relative to the VE supply, ensuring that the filament operates at the correct negative potential. This power supply method, based on an isolation transformer, was very common in older devices using VFD technology. It was especially popular in calculators and other consumer electronics. It is an interesting topic, and certainly one that deserves a more detailed discussion in a future video. To summarize, This panel only requires 9 volts DC and 4 volts DC to display messages and operate normally. The additional 3.3 volt supply on pin 2 is only required if we want to use the infrared receiver and the Bluetooth indicator LED. This supply rail is labeled ever 3.3 volts. The name suggests that it remains powered at all times, even when the unit is in standby mode. Its role is likely to allow the infrared receiver to wake the device and activate the remaining power supplies when needed. The PT6302 also provides two general-purpose output pins, labeled P1 and P2. Originally, only one of these pins was used on the panel. The second indicator LED was instead controlled by a signal arriving through pin 3 of the 13-pin connector. There is an important warning here. This circuit does not include a base resistor on that signal path. If voltage is applied directly without a suitable resistor, the transistor can easily be damaged. To allow the PT6302 to control the standby indicator, we added a 10 kΩ resistor between P2, which is pin 58, and the base of transistor Q901. This modification allows the driver to take full control of the standby LED. By implementing everything described here, we gain complete control over the panel. This includes the display, the indicator LEDs, and even the two buttons present on the front panel. These buttons provide the on and off function and the open drawer function. They can be read using a single ADC input on the Arduino. We chose not to implement that feature in this video, simply to keep the presentation at a reasonable length. We already have several examples on the channel demonstrating how to read keyboard buzzes built from resistor networks with different values. With all of these elements in place, bringing this panel back to life becomes a straightforward and rewarding project.